Manas, okay. Can you please share it with some people later on? Okay.
Yes, sir, I will, sure.
Okay. Okay, we'll start the econometrics portion as of today. We have seen so far the statistics portion, the introductory part, and you will see by and by as we discuss the econometrics part, where all we have used the statistics that we have learned so far. And as I told you, one important part that I would otherwise have taken, it is the maximum likelihood part. The maximum likelihood actually belongs to the estimation. So I'll take it up when we take up estimation. After, according to my course outline also, it comes after wireless only. So after wireless, discussing wireless, we'll take maximum likelihood estimation. But the regularity properties and the asymptotic properties and all, establishing them is very difficult. So we'll assume some regularity conditions exist and discuss an important bound called the Rao-Kramer bound, or otherwise called the Kramer-Rao lower bound for the for the theoretical as well as the estimators. So that's how it goes now. I'll start sharing it. Okay. You can see the slides.
Yes, sir.
Yes, sir.
Okay, we'll begin the econometrics part of it. As always, econometrics has developed from the times of, I think, if I remember right, the term was coined by Rana Frisch, econometrics, way back in the 1940s. And sooner the aim of all the econometricians, the journal in which all the econometricians aim to publish, I have not yet done so far. The Econometrica. Econometrica was born shortly in Cowles Foundation, and that's how it developed. We have seen it in the beginning literature itself, how it started from single equation to simultaneous systems equation, and time series started. Now it's a panel data setup, and it is really spread like anything. It's a wild area, theoretical as well as empirical econometrics. So we start with the definition is nothing but a theoretical quantitative and empirical quantitative approach to address problems posed by economic theory. So in one sentence, as I always explain, so economic theories are quantified in terms of a mathematical model, and then you collect data. You first write the theoretical portions of it, then you have to verify it. You collect data and use statistical inference to draw conclusions about how good your theory has been. So that is the simplest working definition of econometrics. And in this, there can be microeconometrics and macroeconometrics. At this stage, I would like to tell you there is an excellent book written by Trivedi and Cameron and Trivedi on microeconometrics. There you'll realize how much of the statistic that we saw has been used. And that is one thing, that microeconometrics, that's not so prevalent as macroeconometrics. Macroeconometrics, you need out and out time series data knowledge, because econometrics data, macroeconometrics data, aggregate data, macro aggregates, they're all time series data. So to do analysis in that, your time series, understanding of time series properties, both univariate and the multivariate must be top notch. Okay, there are some specialized books. Time series itself became an important field of study. It's a very late addition to the econometrics pantheon. Till 1975, mid 70s, no one took serious note of time series. But then the Box-Jenkins book came, the Box-Jenkins Revolution, and the forecast turned out to be much better than the macroeconometric forecast, the 1000 equation Cowles Foundation macroeconomic model. Nobody could explain that. Remember, in econometrics, we must have been taught about structural form models and reduced form models. Time series are all reduced form models. Their forecasts are much better than the structural form models. So that's how it developed. Then it slowly started as a separate subject. Econometrics was going in one direction, time series was going in another direction. till the time the idea of co-integration came in. I personally consider it as a co-integration, the concept of co-integration, and the paper published by Engel and Granger as the bridge that connected the classical econometrics and the time series econometrics. So now it is that's a concept that you must know. As you read more about co-integration, how useful it is, the utility of it, I leave it to you. Okay, that's how it developed. Why am I saying this? What is microeconometrics? It basically answers some of the questions like this. Okay, before going to this, you must have definitely heard of normally the kind of data set that you may come across are cross-section data, time series data, and the panel data. Cross-section is on individuals, firms, countries, groups, and something like that, and goes on like this, all on individuals. Microeconometrics is basically done with the cross-section data. Time series data consists of data on one particular variable over a year, like GDP from 1955 to 2020. It's like that. Panel data has both cross-section and time series. So the first cross-section, the subscript for the data will always be I equal to 1 This is universal. I hope I have not goofed up anywhere because of my time series habit. So the time series subscripts will always be T equal to 1 to capital T, but panel data will have both subscripts IT. So panel data, also called the longitudinal data or time series of cross section, all refer to the same panel data. It has both. So what all you do in both the things, those things feature in panel data. So that means panel data advantage, you have a huge data set, but along with that huge data set comes huge problems also. So that's an effective area of research. That's an effective area that you should also learn. Panel data will be taught to you in econometrics too. So time series is in IGDR is taught as a separate subject. So this probably will most probably concentrate on cross-section data only. So these are the microeconometrics. Some of the questions you can analyze, like effects on labor supply behavior of a proposed negative income tax, tangible benefits of a voluntary training program, measuring such effects, measurability of moral hazard. What does macroeconometrics do? Usually uses time series data using macro aggregates such as monetary aggregates. And these are some of the questions that are posed. There's a monetary policy regime that targets inflation, impose a real cost in terms of loss of output in an economy. These are all huge research level questions, not easily done in an assignment or a paper. So these are all huge research level questions. It can go as a research level question also. Does corporate tax reduction cut the current recession or contribute to it? These are all important questions that some have been taken from the paper titles also. You can keep on working on this. So it's like this. Another important time series problem that is always my favorite area is the optimal fiscal monetary mix, fiscal policy monetary mix, optimal mix. This is something you can never answer. This keeps on changing, but there is an ongoing research. It's a huge potential to do research. Optimal fiscal monetary mix. It has to be the case that either monetary policy dominates or fiscal policy dominates. Both cannot dominate. So the received wisdom is there will be multiple solutions which can never ever solve. Okay, so this is another question that can be done in macroeconometrics. Theoretical versus empirical econometrics. Goal of most studies in economics is to determine whether a change in one variable causes change in other variable. This is why we are analyzing. There will always be a dependent variable that you collect, and you would like to explain the factors behind the fluctuations in the dependent variable, or factors that explain the variance in the dependent variable. So in this notion, the idea of ceteris paribus, that means everything else remaining constant. Ceteris is never paribus, and all those kinds of things I've been hearing since the time I started learning econometrics. But I'll still continue with the ceteris paribus. This is very important to unravel the causality effect. There's such a causal relationship. Correlation is not causation, of course. Correlation just tells you which way X and Y with any relation. So it does not tell you which causes what. So in econometrics, we hold other factors fixed to uncover causality. This is a very important assumption. And this, of course, theory, you can, I have talked with one or two Nobel laureates also. They always say that no matter how much theory one pronounces or proposes, such theory must be tested on as many data sets as possible and over the years. Then only the theory gets validated. Otherwise, it just remains theory on paper. So that's very important, theoretical versus empirical econometrics. Whenever, if at all, you write a theory paper, always do an empirical analysis. That's why in Econometrica, you always have an application section, empirical section. I think as a policy, they don't accept any paper without an empirical part. Okay. We focus on average or expected response. A ceteris paribus analysis entails estimating expected value of Y. Universally, Y is reserved for dependent variable. That's the response variable. Conditional on W and C. These those of you who are done econometrics can easily see these can be treated as independent variables. What is the expected value of Y conditioned on W and the vector C? So why have I differentiated? This is the ceteris paribus assumption, whose dimension is not important for this discussion. C could be a set of control variables that you'd like to explicitly hold fixed when studying the effect of W on Y, because W is correlated with other factors that also influence Y. So this is exactly what we say when we run a regression of yi on beta 1, beta 2, x1i, x2i, x3i. We would like to see the effect of x1i on y1i holding the effect of x2i and x3i fixed or constant. But sometimes this is meant to understand the ignored. No, that's not ignored. So another way of putting it is after taking into account the role or the effect of x2 and x3, what is the role played by x1 in explaining the fluctuations in the dependent variable, that is y in this case. So that's how it goes. So keep this in mind. Okay. If W is continuous, then interest centers on the partial effect of W on Y, the partial effect of W on the conditional expectation, keeping C fixed. What will be the effect of, what do you mean by, what will be the effect of a change in W on the conditional expectation? That's what we are interested in. And that's called the partial effect. If W is discrete, then we are interested in this conditional expectation evaluated various values of W with the elements of C fixed at some specific values. This is sort of conditional probability. You can see this. But deciding on the set of control variables C is not easy. This is equivalent to saying that what is the set of independent variables that I'm going to have to explain a particular dependent variable. Where are you going to get the set of independent variables? Some are going to, this set, the knowledge is going to come from theory of past published papers or your own theory. That's all one can say. But some are fixed. So say in some studies, you cannot ignore certain independent variables. It's a question of other independent variables, which can vary from country to country, which is not a constant set, which can explain, which can hold good for any situation, any country. There is no such thing as general theory, except probably what Keynes wrote. That's what it says. So if you decide on some C, and if all the elements of C can be observed, then this is another point, that estimating the partial effect of W on EWC is relatively straightforward. Why am I saying if all the elements of C can be observed? Some of the elements in the vector C cannot be observed. For example, education, it can be observed. Ability, how are you going to measure ability? C, on many occasions, we may not observe all the elements of C. For example, in estimating the causal effects of education on wage, we may focus on expected value on the wage, how wage gets affected, condition on education, experience, and abilities. Experience comes with the number of years that you have been in an organization. Education, we are going to see while discussing dummy variables, how education can be measured. Normally, education is measured in terms of number of years, but sometimes this may not work. And education is also sometimes measured as no schooling, or rather school dropout, end of school, graduate, and postgraduates. This is how we normally define education, either a number of years or a threshold level. These are called a threshold level. Schooling, a school dropout, school completed, graduate, postgraduate. You do not normally measure education as 8th dropout, 7th dropout. There is no end to it. So normally it's not done that way. Experience in a particular organization goes with the number of years that you have worked. But how do you measure ability? So that's the problem. While education is observed, ability is not. So even if we obtain a good measure of all the elements of C, we still may not have good measures for Y or W. These always their measurement problem, measurement errors. This is a completely different area of research in econometrics, measurement errors. In econometrics 2, probably you will see if there is a measurement error in the dependent variable, what is the effect? If there is a measurement error in the independent variable, what will be the effect? That is even more serious. Measurement error in dependent variable can be tackled easily, but not the measurement errors in independent variable. There are books written on it. Okay. Now, the first course in econometrics teaches students how to apply multiple regression techniques to estimate ceteris paribus effects of explanatory variables on a response variable. So since we are also a first course in economics, this is also a first course in econometrics. Basically, I'll be concentrating only on this. How do I go about doing it? From the syllabus, you must have seen, I'm going to take you till the single equation setup. What a single equation does not mean simple linear regression. By single equation, I mean there'll be one dependent variable, the set of independent variables. We are going to see the single equation, the problems involved in it. Single equation, the classical linear regression technique with the error assumptions concerning the error term. You relax the assumption concerning the error term. What will be the effect? How we tackle it? And the next one is the so-called dummy variable. Okay. And second thing is people are so enamored of another concept called multicollinearity. I don't know why people are so enamored of it. I'll also spend probably half a lecture on multicollinearity. Okay, perfect multicollinearity does not exist unless you manufacture it, unless your specification itself is wrong. So you don't have to worry about multicollinearities. Multicollinearity, I can tell you, is slowly disappearing from econometrics textbook. But I'll spend about half a class only on multicollinearity. Okay, that's where I intend ending, so that econometrics 2 will take off from where we end. What is that? Single equation to single equation to simultaneous systems equation. Systems equation meaning econometrics 2 will probably start from relaxing the first assumption about X matrix, the deterministic regressor matrix to stochastic regressor matrix, starting from instrumental variables, and from there you'll go to seemingly unrelated regression sure estimation, and from there you'll go to simultaneous systems equation, and after that you'll go to the logistic regression and panel data. That's how I think probably econometrics 2 will proceed. So we will talk about single equation. That is what first course in econometrics is going to talk about that only, in a variety of situations. Okay, we adopt the following. The population model has been specified. An independent and identically distributed sample can be drawn from the population. For example, specifying a model requires us first to define the population of interest. Random sampling is often reasonable for cross-section data. Except when I discuss autocorrelation, I think I will use cross-section data. Very careful about the subscript I'm using. Again, I'm repeating by mistake. I could have used T. Unless I state so, it is the subscript will be I varying from 1 to n. Okay, so cross-section data. What is an example of a typical econometric model? As an example, we can refer to the wage offer function analyzed in labor economics. This is a standard, simple setup that is used heavily in labor economics. The log of wage offer, see the log, another thing that people always commit mistake is the log of the dependent variable. the log of wage offered rather, equal to this set of education, experience, and married, whether you are married or not, plus what is the E? E is called the error term. Here E is called the disturbance term or the error term, which contains unobserved factors that affect wage offers. This only is going to capture all the, this is very important, that's why error analysis. This is what is called whatever assumptions that we make about the error term, including the distributional assumption, everything comes under the huge gap, huge title, misspecification analysis. Misspecification analysis also contains the functional form. The function that the example that I have taken is a very simple linear functional form. So misspecification testing is a catch-all term. You can test everything about your model, and most importantly about the assumption that you're going to make about the error term. So disturbance term or the error term, which contains unobserved factors, that is going to capture the effects of some of the variables, important variables that we could have omitted while explaining the left-hand side variable, that is the wage offer here. Okay, what is our interest in econometrics? Assuming that you have collected data on education, experience, and married life, or married, whether the person is married or unmarried, a single. Our interest lies in estimating the unknown parameters beta 0, beta 1, beta 2, and beta 3. That's it. For deriving the properties that this is enough, you cannot do with one person, with one sample point. So we have to collect a lot of sample points. So you have to attach the subscript I, wage offered I for the ith person or ith individual. It's a function of his education, his experience, and whether he is single or married. Plus EI, where the I subscript refers to, I said as person, it could refer to individual firms, cities, persons, and so on, even countries also. This is a general example. I varies from 1 to n. All assumptions regarding the population model can be stated. What is that? Crucial assumptions involve the error term and the explanatory variables. For example, what does that mean? Conditional expectation of the error condition on the independent variables, experience, education, and marriage is equal to 0. Conditional expectation of the error term is 0. This is one assumption. Is E correlated to the independent variables? This is one of the most crucial assumptions that we have to maintain, that we will be maintaining in single equation analysis. Okay, what will happen when we relax this assumption? It must be relaxed. Single equation does not serve the purpose at all time. Invariably, you need to come out of the single equation setup. Is E correlated to the independent variable? This is a crucial assumption. Okay, now those of you who have done econometrics, what will happen if you relax this assumption?
Non-integrity.
So sometime it happens the estimator may not be blue.
No, one sentence.
Heterogeneity. Non-integrity. Non-endogeneity.
Huh?
Non-endogeneity. It will become
Error term becomes correlated with the explanatory variable.
Yeah, that one term, I am expecting one term.
Inconsistency.
No. Somebody came very near. Have you heard of this?
endogenous. Non-endogeneity.
Endogeneity. Have you heard of the problem endogeneity or simultaneity problem? Simultaneity bias. Have you done this? Econometrics people, have you done simultaneous systems equations?
No, sir.
Yes, sir.
So actually it was in applied econometrics and that was an optional course.
Acha, okay, so this is called simultaneity bias. So econometrics 2 professor will explain to you to the death what it means. E correlated independent variable. This is very, very important assumption. Is the conditional variance of E constant? Okay, this somebody said. This bullet point, what is that?
Homoscedasticity, heteroscedasticity.
Yes, homoscedasticity, heteroscedasticity. Okay, there is another huge thing. Homoscedasticity, the heteroscedasticity is prevalent mostly with cross-section data. At least this was what the idea before Engel's arch-gauge paper came. Those of you have done is called the auto-regressive conditional heteroscedasticity. That paper was published in 1982. To their horror, people realize there is heteroscedasticity even in time series data. How do you approach that problem? You're all doing it very absolutely ad hoc methods. So 1982 Engel's paper is the first paper that tackled this issue in time series data in a rigorous statistical setup. No wonder that paper was quoted by the Nobel Committee. That paper and the co-integration paper, 1985 or 88, I don't remember which year. These two papers were quoted by the Nobel Committee when they gave the Nobel to Engel and Granger. Okay, these two papers, original papers, you must read. You will not believe the 1982 Arch Econometrics paper, how simple it is. You will understand each and every portion of it. Okay. Similarly, the co-integration part, you will understand each and every part of it. You will not believe how simple the paper is. That is why the concept is very important. Okay. So these are all important things that you learn in this important stages in the build-up of time series econometrics, especially. Answers to these questions are relevant for estimating the betas and performing statistical inference. I will revisit all these assumptions in a formal way when we discuss multiple linear regression, or otherwise called classical linear regression setup, which leads to the Gauss-Markov theorem. After discussing some of the properties of the estimators, that will be toward the end. Single equation linear. Yes.
Sir, I have a doubt. Sir,
Yes.
you talked about wage function, that means Aryan wage function.
Mm-hmm.
So basically, so you have included education as explanatory variable.
Mm-hmm.
So there are two possibilities. We can consider number of years of education, which will be continuous, and the second one will be dummy, as you have already explained, like illiterate and literate.
Education. No. Education is never a dummy. Education, we always education. Normally, people refer to as the number of years, and as you point out, yes, it's possible that whether the threshold level also is another approach. Yes. What is the question?
The question is like when to consider which, like if either to consider continuous one or to include dummies of education.
Continuous, depending on the data availability. If you get data on number of years, please take that. But if you don't, then you have to go settle only for the dummy variable type.
So there is, as such, there is no difference. It's just the lack of data.
No difference apart from lack of data. This is a huge problem, especially in a country like India.
Yes, thank you, sir.
If I prefer, I would take only the number of years rather than the graduate threshold level. Okay.
Sir.
Yes, sir.
Yeah.
Sir, in the example, the experience, education, merit example, yes, this one. Sir, what will be the W and what will be the C?
What will be the W and what will be the C?
Yes.
That depends. Suppose you want to consider the education, experience, and merit will go into the C vector.
Okay, and W will go
when it comes to experience, education, merit will be the C vector. W is the dependent variable.
So then when we write expectation of Y given W comma C.
Yeah.
So there also Y is.
Here, this I put W here. Okay, this is very this W is different from this W. Your confusion is whether this W refers to wage.
So what is C in that case, sir?
No. Wait a minute. One. This W that I'm showing here is not wage.
No, I know that.
Yeah.
My question is that like log of the wage was Y. So then what is W and C?
This W is, for example, specifying a model. If you are interested in considering the number of years of education, the effect of one increased level of education on wages, okay, condition or experience in married life given. In that case, C will be experience in marriage, and W here in this case will be the education.
Education, okay.
Okay. Am I right?
Okay. Yes.
That's what I said. Yeah, Kainika, you had a question.
Yes, sir, it got resolved. It was the same question as Rishan's.
Yeah.
Yes.
Okay, our interest lies in unknown parameters.
Sir,
Yeah.
just a simple clarification. Sir, you spoke about misspecification analysis. So, is it about misspecifying the model or error terms? Could you just shed some light on that?
Everything. Misspecification means the error term misspecification, the distributional assumptions about the error specification, the functional form misspecification. Okay, everything. So I said misspecification is a huge catch-all term. You can check about everything about your model, especially the assumptions. Okay, the simultaneity assumption, the endogeneity assumption, everything you can check.
Okay.
Single equation linear model wireless. Yeah.
Sir, can you go to the last slide once? So the assumptions. Yes, sir. In this one, sir, is the conditional variance of E constants at the homoscedasticity and the heteroscedasticity case, sir. In this place, sir, the variance conditional. Sir, does it mean the variance conditional on the explanatory variables and the control variables, or in general also it can be considered for, like, if it is like normal variance is not constant, so will that be heteroscedasticity case, or only for conditional variance not constant we will consider it?
Later on we'll going to answer this question. Conditional variance refers to unconditional variance only.
Okay, sir.
Okay, I'm going to use a particular term to explain this particular question. Wait for a few slides. Okay, why I'm saying that. Single equation linear model and wireless estimation. Single equation linear model is the workhorse of empirical economics. Well, I have written this, but I have to say single equation linear model, of course, is very important. But I can admit this only with a proviso, because that is simultaneous systems equation is the workhorse of empirical economics. Okay. Similarly, in time series analysis, it's not univariate model setup. It's a multivariate model setup, like vector autoregression, and later on vector error correction model along with co-integration. These are the workhorse of, that is the workhorse of macroeconometrics, simultaneous systems, and panel data are the workhorse of simple empirical economics. All three put together. Okay. Single equation linear model is a nice way to start understanding econometrics. Okay, in any first course in econometrics, the method of wireless estimation. We remember our interest is we have to estimate the parameters, unknown parameters, and next perform statistical inference, otherwise called hypothesis testing. Okay. Single equation linear model we'll start with. That's a nice place to start with. In the first course in econometrics, the method, what is the method of estimating the unknown betas? The method is called OLS. It's called ordinary least squares estimation. There's only least squares estimation, ordinary least squares. Later on, we are going to the least squares is the method of estimation. Ordinary least squares has some meaning to that. Then something called the generalized least squares, two-stage least squares, three-stage least squares. It goes on like this. Whether you like it or not, must have read some zillion papers. The authors, what should I say? The attractiveness or the simplicity of least squares is phenomenal. There are also other methods of estimation. Maximum likelihood, we'll see how difficult it is. Maximum likelihood is still coming up. People could do maximum likelihood estimation because of the advancement in the computing system. We will see later why maximum likelihood was not taken up with that much gusto when econometrics started. Okay, because except on one occasion, the likelihood, the objective function becomes a nonlinear, and solving it becomes very difficult. Okay, there are other methods like generalized method of moment estimation, Bayesian estimation, and some people will say estimation by simulation and all those stuff. But the attractiveness of least squares has not died down. I have read zillion papers. All their attempts will be to explain the problem And while when it came to estimating the unknown parameters, they'll always find a way to estimate it using least squares. The best they'll go to is a nonlinear least squares. You must have, some of you must have heard about nonlinear least squares. When you solve nonlinear least squares, they must have heard about Gauss-Newton method. Is it Gauss-Newton? Heard of Gauss-Newton method? And all those stuff. Okay, so in any first course in econometrics, the method of wireless estimation risk extensions are usually learned under the fixed regressor assumption. I'll come to this what is a fixed regressor assumption shortly when I take up the assumption, when I take single equation linear model specifically. Because I am going to, why I'm saying this, we are going to digress a bit and know about certain things before we go into single equation linear model directly. Okay, third bullet point. We learn how to apply multiple regression analysis also to estimate the ceteris paribus effects of exponent variables and response variables. This is simply what is the effect of, say, variable x1 on the dependent variable y, giving other factors, keeping other factors constant. Remember, keeping other factors constant does not mean we have ignored them. We have, after taking into account whatever role they play, what is the role played by x1 and y? That is exactly the meaning. It is still relevant to establish a connection between traditional and the current approach to econometrics. What does that mean? The population model we study is linear in parameters. This is a huge assumption. Linear in parameters. Beta 0, beta 1, beta k are the parameters. They are simply linear. We will never have beta 1 square or beta 1 power b square or exponential beta 1. All these things are ruled out. Our course will be linear in parameters. Why am I insisting on linear in parameters? There could be non-linearity in variables. Yes, there can be non-linearity in variables. If you have non-linearity in variables, essentially the estimation procedure still continues to be least square. Only thing is you may have to do some expansion or correction to that model. Okay, so long as it is linear in parameters, you have no problem. Why x1, xk are observable random scalars. E is unobservable disturbance term or the error term. B0, beta 1, beta k, the parameters which are unknown constant. They are called the population parameters, which are unknown constants. Remember, very important, because when you have to take expectation, you have to remember these are all, after all, constants, unknown constants. We would like to estimate. So this model, OL is 0, is sometimes called the population model. It's convenient to write the model in vector form. Boy, acha, the initial lecture was done. I think precisely asked Thanu to do the matrix algebra part of it. You still remember those things? Hello.
Yes, sir.
How many of you have gone through Johnston's econometric theory, the book?
Sir, we only saw questions from that in undergrad.
Okay, I would like to say the following. This particular book, especially the third edition, which I have, is so good. I still refer to it, by the way. That was the first econometrics book I bought way back in 1980 when I entered this area. Okay, I'm specifying Johnston econometric methods or theory. I don't know. Econometric methods probably. Third edition, chapter 4. उसको ये काम करना, उसको xerox करके रख दो, बस, that's it. Take a photocopy of that 4th chapter, 3rd edition of Johnston. The matrix algebra that is there is absolutely fantastic. Okay, you may need that at many places. When you have any doubt, you can go and refer to it. That will be sort of a ready reckoner that runs about 30-40 pages probably. Everything it has, starting from this to vector differentiation, matrix differentiation, explained beautifully. So that is one thing that you must always read. You, even if it is available of somewhere, purchase it. It's a wonderful book. Okay, there is that book I've referred to. There's another book that I've referred to is called the Judge Griffith 5 authors book, Introduction to Theory and Practice of Econometrics, and Theory and Practice of Econometrics by the same people. That is, the second one is very advanced, And if anyone wants to know the improvements or advances in econometrics literature till 1985, that is the one book. You don't need any other book. So the introduction book is at the introductory level. I have taken some from that book also. So these are some of the books that you should possess for this. And of course, Green and Woolridge, both Woolridge. And some extent Kementa also, and Maddala. Okay, there are too many books here. Okay, this has mean zero. This is vector form. Vector form, this is a scalar. Y is a scalar. Okay, so 1 by k beta k by 1, that is y less 1. This key condition needed for wireless to consistently estimate. Oh, these are all huge word. What is consistent estimate? I'll come to that. Consistently estimate the beta j's is that the error in the population model is mean 0 and is uncorrelated with each of the regressors. These conditions are inviolable. You cannot violate these conditions and still hope to use the classical linear regression model. This is explained as follows in the notation. Expected value, this is the unconditional expectation, is 0 and covariance xj is 0. This means that the error term is not correlated with any of the independent variables. Remember, underline the word uncorrelated. Wireless 2. The zero mean assumption is for free when the regression contains a constant term. This means basically that is unnecessary. When the regression contains, yeah.
So here, are you talking about conditional or unconditional error?
Which one? The wireless 2 unconditional error.
Because earlier we were talking about expectation of E given something. No?
This is the one conditional variance. This one I also told you from here you can always say the unconditional term. Did I say that?
Yes, sir.
How do you come there? You'll see. Okay. Covariance xj, unconditional mean is 0 and it's not covariant with this. Even if by chance consider the following model, exp is not equal to 0, say mu, you can always add it and rewrite it this way. What does this mean?
We are converting it to the we are taking the error as E minus mu and then converting it to find the expectation of that error to be 0.
You are just rephrasing what I've written. Understand the implication behind this. What is the implication behind this? So consider the third bullet.
So if the error is not 0 but a constant, we can just add it to the already given constant and adjust it to make it 0.
What does that mean? Okay, that is one point. What does that mean? Connected to expected value of E cannot equal to 0. What is the expected value of the mean capture?
Sir, we are shifting the data, whole data.
Who is this?
Sir, Hari.
We are shifting the whole data.
Sir, because we are adding mu and then subtracting mu, I think.
What does the error capture, by the way?
The other variables.
This is what I said. Where is the error term? The errors capture. Okay, errors capture. Errors capture basically. Sorry, yeah. Who is this?
So the distance of each observation from the regression line.
You're right, but see, that's not the idea. The intuition here is the following. The errors capture the influence of other variables, the variable that we might have omitted from the set of explanatory variables. Okay, the expectations are supposed to capture that particular effect. Okay? That's why I said concentrate on the error term. If the expected value of that error term is 0, then whatever omitted variables is equal out, you can confidently say that I have not omitted any important variable that I should have otherwise included in the set of explanatory variables. But suppose it is not 0, say mu, what these people say is so long as there is a constant, you can add it to the constant. Now come to the constant. What does constant essentially capture?
Intercept.
What does the intercept essentially capture?
Sir, the value of y when everything else is 0.
The effect of other variable, that also is another answer, because